So hello, I'm Andreas, and I'm here to talk to you about how to model wetting hydrodynamics using data-driven models, as well as using our physical prior knowledge. So physics-informed machine learning modeling for wetting hydrodynamics, a work that was done with Dr. Nikos Sava at the Cyprus Institute. First, some introduction to wetting hydrodynamics. We are dealing with the interaction of very small volumes of liquids on surfaces in the presence of a gas phase. If we zoom in to the contact angle, which is the contact line, which is the line that separates the three phases, we arrive at the smaller and even smaller scales that are governed by different physics, but we are mainly focusing on the macro scale, and whatever information comes from the atomistic scales, the small scales, we introduce them as parameters in our models. Now, I need to convince you why we need to care about droplets. And there are a few applications, for example, water harvesting in dry regions. We have water condensing on these giant nets. Tribology applications, where we add lubricants between mechanical components to avoid friction. So we talk about the texture of the surfaces of the components. Self-cleaning devices, and a very interesting application for us is the microfluidic lab-on-a-chip device, where we use electric fields to move the droplets around. And in this way, we can batch process a large number of chemical or biological samples without the need for any large-scale laboratory equipment. And we carry out similar simulations, but instead of electric fields, we use the chemical heterogeneity on the heterogeneities on the surface to move the droplets around. So here we have darker shaded regions that are more hydrophobic and lighter shaded ones that are more hydrophilic. And naturally, the droplet migrates towards the more hydrophilic region. Now, even though this is a simulation that was carried out with a reduced order model, it still took around 2 days on a high-performance computing node. So you can understand that if we want to simulate many such simulations using more realistic scenarios, DNS, then we are talking about a big computational cost. So our effort here is to simulate relevant configurations, extract the evolution of the contact line, and feed this data into a machine learning model to obtain a surrogate low-order model. And somewhere here, we will also introduce this prior physical knowledge that we have. This can also be done analytically, but only for very small contact angles, meaning very hydrophilic surfaces. And at the end of the day, we want to be able to generate data efficiently. So these surrogate low-order models, we expect them to be much, much faster than DNS simulations, in order to be able to design surfaces with different features for specific applications. Now, the data generation, we use the two-phase Navier-Stokes equations, the continuity, the conservation of momentum with the surface tension term here and the gravity term. As well, the advection of a color function, which identifies the liquid and the gas. And yes, the physical properties are calculated as a weighted average between the physical properties of each phase. And the information for the heterogeneities, how hydrophilic or hydrophobic are is each region of the surface, comes through the boundary conditions. On the right, you see the type of scenarios that we will be simulating. It's the movement of a droplet on an inclined surface, so the droplet moves downhill, and the presence of heterogeneities influences the path of the droplet. And to simulate this flow, we use basilisk, which is a very good choice for us because gives the opportunity for adaptive mesh refinement, and it provides a very efficient multi-grid, built-in multi-grid solver. So to generate our data set, we vary the heterogeneities on the surface using a functional form with 6 parameters, which we change randomly, as well as changing the gravity field and the inclination angle. And overall, we have generated 200 DNS cases with around 80,000 contact line snapshots to be used for the training of the machine learning model. Now, if we follow a fully data-driven approach, our model will not be good enough. That's what we tried, and at least for the amount of data that we are able to generate, a fully data-driven approach will result in inaccurate models. So we thought, how can we introduce our prior physical knowledge into the workflow? So we decided to use a reduced order model that was first suggested by Cox in the 80s. Where this is the form. It has 3 unspecified parameters, lambda, QO, QI, which we can feed into our data. And it is it's basically a function, a complex function of theta star, which has to do with the heterogeneities on the surface, and theta, which is the actual contact angle on the droplet. So, and this model calculates the velocity normal to the contact line. We don't need to go into the details. The main complexity was how to calculate this contact angle, which Nikos Sava was able to come up with an analytical model considering weakly deformed contact angles, contact lines. So we are able to calculate this reduced order model, but as you can see, it has no knowledge of gravity. So our approach here is to train an AI model that introduces gravity once we add it to the reduced order model by Cox. And adding these 2 components together, we want to be able to approximate the DNS velocities. So we continue with the training. We are using the Fourier neural operator as the AI architecture, which basically can provide a mapping between some auxiliary data, the initial solution, boundary conditions, and parameters, whatever we want, and map that to a solution. And this FNO does this mapping through the Fourier space. So if we give the input is lifted into a higher parameter space with operator P, we apply a series of Fourier layers, and then we bring the solution with operator Q down to the output space. And in each Fourier layer, you see that there is one branch where we do a Fourier transform, and we learn the weights of each Fourier mode inside the Fourier space. So that's the novelty here. And what we want to do, basically, we know that the net transport of the droplet due to gravity comes through the first harmonic of the contact line velocity. So as input to our model, we give the first harmonics of the contact angle theta, the heterogeneities along the contact angle, which is theta star. And we include the bond number, which has to do with the gravity. It's gravity over surface tension, and the inclination angle alpha. And we expect to for our model to be trained on to approximate the first harmonic of the difference between the DNS solution and the reduced order model by Cox. So at the end of the day, we want to be able to add this UC to the prediction of Cox to approximate the DNS velocity. And here you see how this looks, the contribution of each component, starting from the blue line, which is the reduced order model, you see that it has no idea how gravity will pull the droplet. We calculate the AI model, which is shown in a red dashed line. If we add these two together, we get the red solid line, which, as you can see, it is in a good agreement with the reference DNS solutions. And since we are calculating a component of the velocity of the contact line, what we want is actually to come up with an error that has to do with the position of the droplet. So we use the Fréchet distance, which is a measure of the similarity between the curves, taking into account the location and ordering of points along the curve. And we normalize this measure with the average diameter of the droplet. So basically, if you consider, if we have two perfect circles, if these circles do not overlap, this Fréchet error would be larger than 100%. And if they overlap, it will be less than 100%. Here we see some very simple testing scenarios that we tested our workflow. You see on the left, we have a homogeneous surface. On the right, we have stripes with alternating wettability. And on the right, you see a checkerboard pattern where our droplet gets stuck on the features, and therefore the Fréchet error is so low. A more challenging scenario will be this one, where the stripes are a bit diagonal, and you can also see the path of the centroid of the droplet. And it's clear that our method approximate both the path and the droplet shape, and it's in a very good agreement with the reference results. And if we see how it performs by changing the bond number and the inclination angle, first, the top row, you can see as the inclination angle increases, of course, the results become the droplet position, the accuracy falls, but at least the path that is followed by the droplet is in a very good agreement with the reference results. And now if you go to the bottom row, we change the bond number, the magnitude of gravity, and we can see that as we increase, again, accuracy is reduced. And the final case with a bond number of 8, we have a very large error, and this is basically because we train our model up to a bond number of 5. So we get these large errors because the parameters that we use are outside our training distribution. So overall, we are able to couple this analytical model with a data-driven counterpart, and this is more general. It doesn't have to do with wetting. It can be for any problem. And in this way, we have widened the applicability limits of the reduced order model. And we see that at least the droplet path is captured accurately, and unless we step outside our training distribution. And the resulting workflow is orders of magnitudes faster than traditional DNS solutions. So the main gain here is that we can use this workflow for inverse designing. So this is our funders race, the Center of Excellence race. Many people here work on this. And the CIMEA simulation for exascale for engineering applications, another EU program. And a last comment, there will be tomorrow a talk on controllable droplet transport, where we basically try to it's an inverse design problem. We try to tune the heterogeneity so that we get a specific droplet path using these types of workflows. And another online training event for physics-informed machine learning at the Cyprus Institute, where whoever wants can participate. Thank you very much. And please, if you have any questions.